Imagine a world where time moves differently depending on where you are. Gravity, the force that keeps us grounded, also warps time. But why does gravity slow down time? The relationship between gravity and time is a cornerstone of modern physics. From the ticking of our clocks to the movements of galaxies, gravity's influence on time is profound. We'll delve into the theory of general relativity to uncover why gravity affects time. By the end, you'll see how this knowledge impacts our daily lives and shapes our understanding of the cosmos. So let's embark on this journey through time and gravity. Prepare to have your perception of reality stretched and your curiosity ignited. Albert Einstein's theory of general relativity revolutionized our understanding of gravity. Before Einstein, gravity was simply a force that pulled objects towards each other. Isaac Newton's laws explained this quite well. But Einstein saw gravity differently. Einstein proposed that gravity isn't just a force, it's a curvature in space-time. Imagine space-time as a stretchy fabric. When a massive object like the Earth sits on this fabric, it creates a dent. Smaller objects fall into this dent, which we perceive as gravity. This bending of space-time also affects time. According to general relativity, time moves slower in stronger gravitational fields. This means that the closer you are to a massive object, the slower time passes for you. Understanding general relativity is key to grasping why gravity slows down time. To understand how gravity affects time, let's imagine a simple scenario. Picture two clocks, one on top of a mountain and one at sea level. The clock at sea level experiences stronger gravity because it's closer to the center of the Earth. The clock on the mountain, being further away, experiences weaker gravity. According to general relativity, the clock at sea level ticks slower than the one on the mountain. This difference is tiny, but it's real. Over a year, the sea level clock would be slightly behind the mountain clock. This phenomenon is known as gravitational time dilation. Another way to visualize this is to think of time as a river. In areas of strong gravity, the river flows more slowly. In areas of weak gravity, it flows more quickly. This stretching and squeezing of time happens everywhere in the universe. Even though we don't notice it in our daily lives, gravitational time dilation has significant effects. You might think that time dilation only matters to astronomers and physicists, but it has real-world implications. One everyday example is the Global Positioning System, GPS. GPS satellites orbit the Earth at high altitudes where gravity is weaker than on the ground. Because of gravitational time dilation, the clocks on these satellites tick faster than those on Earth. Engineers must account for this difference to ensure the GPS provides accurate positioning information. Without these adjustments, your GPS could be off by several miles. Another example involves flying in an airplane. When you fly at high altitudes where gravity is slightly weaker, time moves a tiny bit faster for you compared to someone on the ground. Over long flights, this effect is minuscule but measurable. These everyday examples show that time dilation isn't just a theoretical concept. Section 5. The role of gravity in GPS systems. The Global Positioning System, or GPS, is a marvel of modern technology. It helps us navigate, find locations, and even track weather patterns. But did you know that GPS relies on an understanding of gravity and time? GPS satellites orbit the Earth at about 20,000 kilometers above the surface. At this altitude, the gravitational pull is weaker than on the ground. This means the clocks on these satellites run slightly faster due to gravitational time dilation. If this difference weren't accounted for, GPS readings would be inaccurate. Engineers use Einstein's equations to adjust the satellite clocks. They slow them down a bit to match the pace of time on Earth's surface. This ensures that the GPS system provides precise data. Without these adjustments, your GPS could lead you astray by several miles each day. This application of general relativity shows how essential an understanding of gravity and time is. Section 6. The effect of gravity on aging. The idea that gravity affects aging might sound like science fiction, but it's true. According to general relativity, time moves slower in stronger gravitational fields. This means that people who experience stronger gravity age more slowly. To illustrate this, let's consider two twins. One twin lives at sea level, where gravity is stronger. The other lives on a high mountain where gravity is weaker. Over their lifetimes, the twin at sea level will age slightly more slowly than the twin on the mountain. The difference is tiny, but it's real. This effect becomes more pronounced in extreme conditions. Astronauts aboard the International Space Station, or ISS, experience weaker gravity than on Earth. Time moves faster for them compared to people on the ground. Over a 6-month mission, the difference is minuscule, but over many years it adds up. Near a black hole, the effect is dramatic. The gravitational pull is so strong that time almost stops. Section 7. Black holes and time. Black holes are some of the most intriguing objects in the universe. They are regions of space where gravity is so strong that not even light can escape. This intense gravitational pull also has a profound effect on time. Near a black hole, the gravitational field is incredibly strong. According to general relativity, this means time moves extremely slowly. If you were to watch a clock fall into a black hole, you would see it tick slower and slower as it approached the event horizon, the point of no return. For someone falling into a black hole, time would appear normal from their perspective, but to an outside observer, their fall would seem to take an eternity. This extreme time dilation means that from the outside, they'd appear frozen in time at the event horizon. Black holes provide a natural laboratory for studying the effects of gravity on time. They challenge our understanding and push the boundaries of physics. Section 8. Gravity's impact on the universe. Gravity's influence on time isn't limited to Earth or even our solar system. It shapes the entire universe. From the formation of galaxies to the behavior of stars, gravity and time are deeply intertwined. In the early universe, gravity played a crucial role in forming structures. Matter clumped together under its pull, forming stars and galaxies. As these massive objects formed, they curved space-time around them, affecting the flow of time. This process continues today, influencing everything from planetary orbits to the expansion of the universe. The concept of cosmic time dilation is also fascinating. In regions of intense gravity like clusters of galaxies, time moves slower compared to less dense areas. This means that different parts of the universe experience time at different rates. Gravity's impact on the universe is a testament to the interconnectedness of all things. It shows how fundamental forces shape not just our lives but the very fabric of reality. Section 9. Interesting facts about gravity and time. The connection between gravity and time is full of fascinating tidbits. Here are a few interesting facts that highlight this relationship. First, did you know that time moves faster on the top floor of a skyscraper than on the ground floor? The difference is tiny, but measurable. This is due to the weaker gravitational pull at higher altitudes. Second, astronauts aboard the International Space Station experience time dilation. They age slightly slower than people on Earth. Over a 6-month mission, they gain a few milliseconds compared to us. Another interesting fact involves the center of the Earth. Time moves slower at the core compared to the surface. The intense gravitational pull at the core causes this effect. If you could live at the Earth's core, you'd age more slowly than someone on the surface. These facts show how gravity and time are woven into the very fabric of our existence. Section 10. How understanding gravity and time affects us. Understanding the relationship between gravity and time has practical benefits. It helps us navigate, explore space, and even understand our own aging process. But beyond these practicalities, it also enriches our appreciation of the universe. For one, it allows us to create accurate navigation systems like GPS. By accounting for gravitational time dilation, we can pinpoint locations with incredible precision. This technology has transformed how we travel, communicate, and conduct scientific research. In space exploration, understanding gravity and time is crucial. It helps us plan missions, predict the behavior of celestial bodies, and even search for extraterrestrial life. The knowledge gained from studying gravity and time dilation informs everything from satellite trajectories to the search for habitable planets. On a personal level, this understanding deepens our appreciation of time itself. Knowing that time is malleable, shaped by gravity, adds a layer of wonder to our daily lives. Section 11. Conclusion. The marvels of gravity and time. In conclusion, the relationship between gravity and time is one of the most intriguing aspects of our universe. From the theory of general relativity to the practical applications in GPS and space exploration, this connection shapes our understanding of reality. We've explored how gravity bends space-time, causing time to slow down in stronger gravitational fields. We've seen how this affects everything from our daily lives to the behavior of black holes. And we've marveled at the cosmic implications of gravitational time dilation. Gravity and time are not just abstract concepts, they are fundamental to the fabric of existence. They remind us of the complexity and beauty of the cosmos. So next time you look at a clock or gaze at the stars, remember the unseen forces at play. Think about how gravity is shaping time, subtly influencing every moment.